talked about spring forces, we've talked about frictional forces, we've talked about drag, and very briefly about lift. There's one other force model that we'll end up using quite a bit, or one other type of force that you end up encountering quite a bit in a mechanics space, and that is the gravitational force. So let's talk a little bit about gravity, and in particular I want to talk about gravity first from a sort of fundamental perspective, and then make a connection between that and the ways that we often think about gravity when we're doing modeling close to the Earth's surface. So Newton's universal law of gravitation Newton says that if you have two masses, m1 and m2, and here I'm talking about point masses, so I've somehow abstracted from some extended object down to a point mass, and they're each located at some position in space. So let's say m1 is located at r1, and wherever m2 is located at r2, that m2 exerts a force on m1, and in particular that force is an attractive force, so the masses attract each other, and there are a couple of things that determine that attraction. One is, of course, the direction of the attraction, so m1 wants to go towards m2, so m1 is going to go in the direction, or is going to be pulled in the direction of r2 minus r1. And furthermore, the magnitude of that interaction, or the magnitude of that force, depends on how big m1 is, depends on how big m2 is, and depends on r2 minus r1. So let's think about that a little bit. The gravitational force that 2 exerts on 1 has a magnitude and also has a direction. Let's talk magnitude first. The magnitude is the universal gravitational constant, which is just a number, and you can look up what that number is, times the product of m1 and m2. So if you increase the size of this mass, the interaction is stronger. If you increase the size of this mass, the interaction is stronger. And then that's divided by the distance between the two objects squared. So this is r2 minus r1 vector magnitude squared. Okay? That's what the magnitude is. The direction that that force applies, the force that m2 exerts on m1, attracts m1 to m2. In other words, it's in the direction of r2 minus r1. So if I wanted to write the direction of r2 minus r1, I write r2 vector minus r1 vector. That's a vector that's in that direction. And then I would divide by the magnitude of r2 minus r1 in order to turn that into a unit vector, right? So this is a unit vector that points from r1 to r2. Okay? And I, of course, could combine terms here and get g times m1 times m2 times r1 vector minus r2 vector minus r1 vector, all divided by the magnitude of r2 minus r1 cubed. Key things to note here, one is that the actual magnitude of the force depends on the distance inverse. It's an inverse square law. It depends on the distance between the two squared in the denominator, and depends on the product of the two in the numerator. Okay, now this is a general expression for what the gravitational force is. We often see a different expression for what the gravitational force is. You often see that the force of gravity is minus mg j hat. And if you actually think about it, that seems very different from this expression, right? That does not seem to be the same thing as the sort of Newtonian gravitational expression that says it's 1 over r squared and depends on the product of things. Well, but the reason why that you seem to have this seeming disagreement here is that this is a model that only applies near the Earth's surface. And in particular, what this model does is basically say that R1, which is where the mass, the first mass is, and R2, where the second mass is, neither of those is really changing very much. So if this were sort of the center of the Earth, right, so here's the Earth, R2 might be the center of the Earth, R1 might be your location on the surface of the Earth. What this model says is that basically you're not moving around very much. In particular, the distance from you to the center of the Earth is not really changing. And furthermore, the distance from you to the center of the Earth, is always pointing down, because if you sort of zoom in here enough, when you zoom in on that, here's you standing on the surface of the Earth. No matter how you move back and forth, pointing towards the center of the Earth is down, right? So the direction is always down. And no matter how much you jump up and down, the distance of you from the center of the Earth is basically the same. So in fact, if you think about it, this g that's here actually could be rewritten, just the size of it at least, as g times the mass of the Earth divided by the radius of the Earth squared. And at that point you can start to see, okay, the gravitational force is g times the mass of the Earth times, say, your mass, the mass of the object, right? G times m1 times m2, divided by the magnitude of r1 minus r2 squared. So r sub e is the distance from the center of the Earth to the person. And then, of course, the direction is j hat, and j hat is the same as the direction from the center of the person to the center of the Earth.